Chapter 9, Calculations from Chemical Equations. This chapter is going to completely focus on stoichiometry. And stoichiometry is the area of chemistry that deals with the quantitative numerical relationships between reactants and products, between reactants and reactants, or between products and products in a chemical equation. So basically, it's finally the field of chemistry that if I use 10 grams of A, I can calculate how many grams of B I need, and then I can figure out how many grams of C and how many grams of D I will produce. And so this is a very mathematical chapter that allows us to explore the numerical relationships between all the reactants and products in the chemical equation. It's absolutely essential that the chemical equation is balanced, because if the chemical equation is not balanced and the coefficients are not correct, and the coefficients that you use to get your stoichiometric ratios will not be correct, and therefore everything will be wrong. And so it's absolutely essential that you always double check and make sure that your chemical equation has been balanced before you apply stoichiometry. Alright, so if we look at our first reaction, hydrogen gas reacts with oxygen to form water. There are 6 possible mole ratios here. We use 2 moles of hydrogen for every 1 mole of oxygen that we use. We use 2 moles of hydrogen for every 2 moles of water we produce. We use 1 mole of oxygen for every 2 moles of water produced. We use 1 mole of oxygen for every 2 moles of hydrogen used. We produce 2 moles of water for every 2 moles of hydrogen that we use, or we produce 2 moles of water for every 1 mole of oxygen used. And those are the stoichiometric ratios that show the ratios in which you're using reactants compared to each other, or when you're making products compared to the reactant. So if 4 moles of oxygen are present, how many moles of water can be formed? Well, it's a 2-to-1 ratio. So you will make 2 moles of water for every 1 mole of oxygen that you have. If you have 4 moles of oxygen and you produce 2 moles of water for every 1 mole of oxygen consumed, we will produce 8 moles of water. Those ratios hold throughout the whole reaction. Given the following balanced chemical equation, write the mole ratio needed to calculate the moles of water produced from 3 moles of carbon dioxide. So how many moles of water will be produced from 3 moles of carbon dioxide? Well, for every 1 mole of carbon dioxide that we burn, we produce 2 waters. Let's double check and make sure it's balanced. 1 carbon on the left, 1 carbon on the right. 8 hydrogens on the left, 8 hydrogens on the right, 4 in methane and 4 in the 2 waters. 2 oxygens on the left, 2 oxygens on the right. So it is indeed a balanced equation, and it's a 2-to-1 ratio, so I will produce 6 moles of water when I consume 3 moles of carbon dioxide, because it's a 2-to-1 ratio. How many moles of hydrogen do I need to produce 3 moles of water? Well, that is a 4-to-2 ratio. I will consume 4 moles of hydrogen for every 2 moles of water produced. And if I want to produce 3 moles of water, I need 4 for every 2. I need 6 moles of hydrogen. And this is the only new part of this chapter. The stoichiometric ratio, when you're comparing a reactant and a reactant, or a reactant and a product, or a product and a product. All the other conversions were from chapter 7. So given the following balanced chemical equation, what is the mole ratio needed to calculate the following? The moles of potassium chloride produced when 4.5 moles of oxygen are formed. First, double check, make sure it's a balanced equation. I got 2 potassiums on each side, 2 chlorines on each side, and 6 oxygens on each side. It is balanced. And the ratio that I care about is that I produce 2 moles of potassium chloride for every 3 moles of oxygen produced. Therefore, if I produce 4.5 moles of oxygen, I will produce 3 moles of potassium chloride, because I produce 2 moles of KCl for every 3 moles of oxygen produced. Stoichiometry is always a mole-to-mole ratio. It could be a molecule-to-molecule ratio, but it's very rare that you're ever doing chemistry on a molecular level where you just have a handful of molecules. That's extremely rare, extremely specialized chemistry. So most normal chemistry is mole-to-mole ratios. All right, so let's do some more. How many moles of carbon dioxide will be produced by a reaction of 2 moles of glucose, given the following balanced equation? Even though it says it's balanced, let's double check them. 6 carbons on the left, 6 carbons on the right. 12 hydrogens on the left, 12 hydrogens on the right. 6 plus 6 times 2, that's 18 oxygens on the left. 6 times 2 plus 6, 18 oxygens on the right. It is balanced. And the important stoichiometric ratio is 6 to 1. I produce 6 carbon dioxides for every 1 glucose consumed. Therefore, if I consume 2 glucose, I will make 12 moles of carbon dioxide. How many water molecules are produced when 0.01 moles of oxygen reacts? And given the following balanced equation. Now we're going to have to do one more step because they want an answer in molecules. And so, I first convert moles of oxygen, and I do stoichiometry, and I see that I produce 2 moles of water for every 1 mole of oxygen consumed. But they want an answer in molecules, so then I have to multiply by 6.022 times 10 to the 23rd molecules per mole to get an answer in molecules. So I would have 0.02 moles of water, which is 1.2 times 10 to the 22nd molecules of water. How many moles of aluminum are produced when 0.5 moles of oxygen react, given the following balanced equation? Well, if I have 0.5 moles of oxygen, and I'm consuming 4, and that's the problem, that produce should be consumed. Aluminum is a reactant. Reactants get consumed. Products get produced. So this chapter has a few typos. So how many moles of aluminum are consumed when 0.5 moles of oxygen react? Well, it's a 4 to 3 reaction. So you consume 4 moles of aluminum for every 3 moles of oxygen consumed, which means we will consume 0.67 moles of aluminum to react with 0.5 moles of oxygen to make our aluminum oxide. What mass of hydrogen can be produced when 6 moles of aluminum reacts with hydrochloric acid? And now they want a mass. So first, we'll do stoichiometry. I have 6 moles of aluminum. And let's double check, make sure it's balanced. 2 aluminum, 2 aluminum. 6 hydrogens, 6 hydrogens. 6 chlorines, 6 chlorines. It's a balanced equation. And so my stoichiometric ratio of interest is I produce 3 moles of hydrogen for every 2 moles of aluminum consumed. So that's 6 times 3 divided by 2. I will have 9 moles of hydrogen. Then they want an answer in mass. So I convert, and hydrogen is H2, so that's 1.008 grams per mole times 2, because there's 2 atoms of hydrogen in a hydrogen molecule, if we remember from chapter 7, which gives us 18 grams of hydrogen gas produced. How many moles of water are produced when 325 grams of octane are burned? Well, first we have to convert grams of octane to moles of octane. And we look up with our trusty periodic table. 8 times 12 is 96, plus 18, that puts us to about 114 grams per mole. It's 114.2 grams per mole. And we convert grams of octane into moles of octane. And now we do a stoichiometry. We double check, is this balanced? 16 carbon, 16 carbons. 36 hydrogen, 36 hydrogen. 50 oxygen. 16 times 2 gives us 32 plus 18, 50 oxygen. It is balanced. And so we produce 18 moles of water for every 2 moles of octane consumed. So 18 over 2 is the stoichiometric ratio. We produce 18 moles of water for every 2 moles of octane that is consumed in the reaction. And we get 25.6 moles of water produced. How many grams of silver nitrate are needed to produce 0.25 moles of silver sulfide? Well, We have 0.25 moles of silver. We want to produce 0.25 moles of silver sulfide. That's a 2-to-1 ratio. You will consume 2 moles of silver nitrate for every 1 mole of silver sulfide produced. And then we convert to grams. Silver, if we add up silver, nitrogen, and 3 oxygens, we get 169.9 grams per mole. So I need 85 grams of silver nitrate to make this reaction happen. And let's double check, make sure it's a balanced equation so we know we're right for sure. 2 silvers, 2 silvers, 2 nitrates. Remember, when you balance, polyatomics stay together. So that's 2 nitrates, 2 nitrates, 2 hydrogens, 2 hydrogens, a sulfur and a sulfur. Yes, it is balanced. How many grams of nitric acid are required to produce 8.75 grams of dinitrogen monoxide from the following reaction? Let's make sure if it's balanced. 4 zinc, 4 zinc. 10 hydrogens, 10 hydrogens. Here we have 8 nitrates, and here we have 10 nitrates, and some of the nitrates broke up, so that makes it harder. So we have 8 nitrates and 8 nitrates, and there's 2 more here, so there's 2 nitrogens and 6 oxygens still unaccounted for. So we look over here, we have 2 nitrogens, then 1 plus 5, 6 oxygens, so it is balanced. And we convert our grams of dinitrogen monoxide into moles of dinitrogen monoxide. 14 plus 14 plus 16 gives us 44 grams per mole. And we see the stoichiometric ratio of importance is 10 to 1. We consume 10 moles of nitric acid for every 1 mole of dinitrogen monoxide produced. Remember, no coefficient means 1. And then we convert back to grams, nitric acid. You add up a hydrogen, a nitrogen, and 3 oxygens, 1 plus 14 plus 16 plus 16 plus 16 to get 63 grams per mole. And we get 125 grams of nitric acid required. How many grams of chromium-3 chloride are required to produce 75 grams of silver chloride using the following reaction? Well, we're going to produce 75 grams of silver chloride. We convert that to moles by adding up a silver and a chlorine from the periodic table. Now, stoichiometrically, we need 1 mole of chromium-3 chloride for every 3 moles of silver chloride produced. So it's a 1 to 3. We need 1 mole of chromium-3 chloride to produce 3 moles of silver chloride. Convert back to grams. We add up a chromium plus 3 chlorines to get 158.4 grams per mole. And we get 27.6 grams of chromium-3 chloride. Limiting reactants.